So, good morning, everyone. Let's get started. So it's a pleasure to welcome Jia Liu from Princeton as our ITC Colloquium speaker this week. Let me briefly introduce the speaker. So Jia got her PhD at Columbia University, New York in 2016 and has been an NSF postdoctoral fellow in Princeton ever since. And Jia is mainly working on cosmology, structure formation, and how to measure structure formation via CMB lensing, weak lensing, and things like that. And one of her focuses are neutrinos and their effect on structure formation, which is also the topic of her talk, Cosmology with Massive Neutrinos. So let's welcome her to the ITC.
Thank you, Rainer. Thank you guys for having me here. If you don't know anything about neutrinos, from the font, you can already see some conclusion. It's a particle that moves really fast. Okay, I'll tell you about neutrinos today. And it's not working. Technical difficulties. Sorry. Okay. Massive neutrinos. So in the past century, particle physicists did a really good job to complete the standard model of particle physics. So here are the quarks and the leptons and the four force-carrying gauge bosons and the Higgs boson that gives mass to other particles. So in this original picture of standard model of particle physics, the three neutrinos had zero mass. It is not only just because they look like they have no mass, they move really fast, they move like they move like the light, but also because we only see left-handed neutrinos. Through the Higgs mechanism, we simply don't know how to give mass to these left-handed only particles. But then there comes the solar neutrino problem. It goes like this. We know how the nuclear reactions happen in the sun. In the center of the sun powers the sun. And then we know how bright the sun is, and then we know how far it is. Therefore, we know the amount of electron neutrinos we should expect on Earth. However, we only see a third of them. So many people were blamed during that time. First, we astronomers are not particularly famous for our accuracy. So getting it wrong by a third, it doesn't seem to be a big deal. Second, neutrinos are not very easy to detect after all. So in the particle physics experiment, missing 2/3 of them, maybe somewhere there's a problem. But as the story goes on, turns out both particle physicists and astronomers, surprisingly, were correct. So the problem is at neutrinos. The answer is neutrino oscillation. So during their production, and then towards the Earth, electron neutrinos were produced in the center of the sun, and on their way to Earth, the neutrino goes through flavor oscillation, where they're turned into other flavors of a neutrino, muon or tau neutrino, back and forth. So by the time they reach Earth, only 1/3 of them remain electron neutrino, and that is what we detect. So from neutrino oscillation, we can make some conclusions. This can only happen if there's a mixing between the neutrino mass eigenstate, nu1, nu2, nu3, and then their flavor eigenstate, nu e, nu mu, nu tau. So from this, we can tell that nu1, nu2, nu3, they must be all different, meaning only one of them can be zero. Therefore, the sum of them must be non-zero. And of course, this discovery was granted a Nobel Prize recently, and that is the foundation of the cosmology work. So from the neutrino oscillation experiment, one is from the atmospheric neutrino oscillation, and there's the solar neutrino oscillation I mentioned just now. We know two splittings of the mass square. So there's this one and another one, and one is smaller and one is bigger. However, because we only know the absolute value of this mass square difference, there's another way to arrange the neutrino masses. We call them inverted hierarchy, where instead of one big mass, two small masses, you have two bigger masses and one small mass. The problem with this picture is that we still don't know the mass of the lightest neutrino, therefore we don't know the total mass of them. However, if we just assume this question mark to be 0, we can already say something about their total mass, which is 0.06 eV for the normal hierarchy and 0.1 eV for the inverted hierarchy. So why do we care about neutrino masses? So is that simply just a number to put on to the chart so we don't embarrass ourselves, or is there some other reason? So if you put all the fermions to this chart, a scale of different energies, this is what you see. So here are the quarks, and here are other leptons, tau, muon, electron. So they are pretty much clustered around this region. If I put all the neutrinos on this plot, the 3 mass eigenstates, so 2 different hierarchy, they're down here. So there's a very uncomfortable 6 orders of magnitude gap in between them. So why is this? What is the mass generation mechanism behind neutrinos that they're so light and so different from the rest of the fermion particles? So of course, particle physicists are already trying to figure this out. The typical technique they use is the tritium beta decay. So here you have one tritium particle, which is just hydrogen with 2 extra neutrons, and it goes through beta decay and then generate one helium-3 particle and then one electron antineutrino and the electron. So by measuring the electron energy, you can say something about the neutrino mass. So here is the electron kinetic energy, and this is the count. Just looking at the end point of this spectrum. So this is what you expect from 0, and this is if neutrinos have mass. And the difference between them are simply taken away by the neutrino, rest mass. So what is our constraint on the total mass of neutrinos now? So let's look at particle physics. So through the beta decay experiment I just mentioned, we have an upper limit of 2 eV right now. What is the forecast? So this is a Katrina experiment, just went online this past June. It's an experiment in Germany, and this is 200-ton spectrometer they're using, and then being carried through the city from where it was made to the lab. And which is really shocking, because in order to carry it, you have to measure the clearance to buildings down to centimeter. So from Katrina experiment, we expect the constraint will lower to 0.2 eV, 1 order of magnitude lower, about 3 years from now. How about from cosmology? Combining Planck CMB lensing, and baryonic acoustic oscillation, Planck, from their recent result, they already published a number 0.12 eV, which is order of magnitude lower than the particle experiment. How about in the future? Many large cosmology surveys are coming online soon. Combining LSST, DESI, and CMBS4, for example, you will expect an order of magnitude improvement, 0.03 eV. So if you compare this number to what I put here just for your note, 0.06 eV for normal hierarchy and 0.1 eV for inverted hierarchy, this says with future cosmology surveys in the next 10 years, we'll almost for sure, if not discovery, we'll have some hint of the neutrino mass. So why is cosmology doing so well? That will be the next part of my talk. By the way, please interrupt me whenever. Massive cosmic neutrinos. Okay, this is a plot you probably use a lot yourself to show the public. I only want to point out 2 important epochs. One is the CMB, happened 380,000 years after the Big Bang, where the photon decoupled from the rest of the particle soup and string out of the particle soup. But then, an earlier time, similar event happened. That was the CNUB. That was 1 second after the Big Bang, around here, where instead of photons, but it was neutrinos free stream out of the particle soup. So how about observations? So for CMB, in the past several decades, we already see 3 generations of amazing space satellites, from COBE to WMAP to Planck. You can see that the resolution is getting better and better. How about CNUB? Nothing. So what's going on? So we are actually becoming very good at detecting neutrinos. So here are the neutrino sources we detect on Earth. Here are the energy of them, and then here's the flux of them. So here are the solar neutrino I mentioned, and the supernova neutrino, 1987A. And here are the atmospheric neutrino and the neutrino from AGN that we recently heard from the ice cube. So we are actually very good at detecting neutrinos. What about the cosmic neutrinos? If you put them on this chart, they lie here. So in terms of number, there are actually a lot of them. Many matter of magnitude than other neutrinos. However, if you look at their energy, they are so low in energy that they simply can't shake the nucleons in our detector. That is why we haven't detected them yet.